yeah, if the sun became a neutron star, which is it would have a kilometer or two radius or diameter. I'm not sure, but the black hole is much smaller than that. Yeah,
like 10 kilometers, but
10 kilometers for the neutron star.
Yeah,
of the sun.
Yeah, yeah. I forget. We measured one with NICER. I forget the exact number we got.
I mean, so a neutron star cannot get, well, if it's got more than like 2.5 solar masses, then it collapses down to a black hole. And a black hole. And by the way, you know, people talk about Hawking radiation from a black hole. It evaporates. So according to Hawking and company, the black hole has a mass, a radius, and a temperature. And because it's got a temperature, it should emit black body radiation. However, normal black hole is colder than the microwave background it's sitting in, and therefore it won't radiate net. It will absorb radiation and get bigger. To actually radiate itself away, it has to start from a very small size.
Well, we'll wait for the universe to cool down.
Yeah, yeah. Eventually, the universe will cool down enough, right? And then we'll
another interesting one where the fellows were talking about, again, recent college. I can't remember what it was. They were looking at white dwarfs, and as white dwarfs accumulated mass, and of course, as it accumulates mass, it gets smaller.
Mm.
And they were looking at the point of saying, when does it turn into a neutron star? And they said that they were actually looking at that process and thereby determining when a white dwarf becomes a neutron star.
That's interesting. So can it do that without, do you think, without initiating a type 1a supernova where it goes kablooey? It can just gracefully do like a phase change from a white dwarf to a neutron star?
From what I saw, this is the initial observations, and they're going,
Well, so Joanne, there was something about, you know, white dwarfs coalescing, two white dwarfs spiraling in and coalescing, and then having enough, and then becoming a black hole. So one way of forming them. But
a black hole, not a neutron.
Let me comment on that, because there's actually a paper in preprint that I'm a co-author on, where we looked at data from TESS, and we looked at type 1a supernovae, and we looked for evidence of the companion from which the white dwarf would be accreting, and we didn't find it. And we think that we're seeing, we've looked hard enough. We think what we're seeing is evidence that the 1As really are these these double white dwarf systems coalescing, and that when they coalesce, they don't collapse, they detonate.
Mm.
And
the phase change is not, the phase change is not gentle, it's a catastrophic event, huh?
Well, yes, there's enough nuclear energy still in the carbon and oxygen that a white dwarf is made of, that when it fuses to iron, it's sufficient to blow the whole thing apart. So it's a thermonuclear bomb.
And that's how the iron gets out and into planets and so on, right? Because it doesn't come, it comes from exploding stars.
Yeah, that makes sense. So it's like it's almost like a white dwarf can gradually creep up to a critical mass that is in some ways analogous to the critical mass of fissile material.
Yes.
That's awesome.
And we also believe now the evidence that we see of type 1As is that they are the ones we've looked at appear to be these double white dwarfs, but we also see cataclysmic variables where a white dwarf is accreting matter from a regular star. And we also believe that those eventually detonate and become supernovae, although now we're getting a little puzzled about how to tell the difference between the regular 1As and whatever these are, and maybe we can't. But it is not thought that when you add matter to a white dwarf, it collapses into a neutron star. It is thought that to make a neutron star, you have to have the core of a star that already has fused to iron. And then when that collapses and makes a type 2 supernova, you get a neutron star, or if it's big, a black hole in the middle.
So, John, can I ask you something about these type 1a supernovae, because you seem to know about those well. So, as I understand, they are supposed to be the sort of standard candles that enable to see them in very distant galaxies, and because they're supposed to be all have the same sort of luminosity curve to tell how far away they are, and hence get the scale of the expansion. And that was a discovery of dark energy, right? But the question I have is whether we really know that supernovae of this type from first generation stars or second or third generation stars actually are all the same. Because if they're not, that would change scale.
Yes, and there has been a great deal of empirical work on this. At one time, it was thought that they really were standard candles, and then when enough had been studied, we came to understand that they aren't all the same amount of energy. They aren't the same luminosity, but you can that there's a close correlation between how fast they rise in brightness and how bright they are. And so you
their intrinsic brightness, yeah.
Yeah, and so you calibrate that using supernovae at known distances, where you infer their distance by other means, which you always have to do to do the standard candle stuff. And that was what led to the discovery that the deceleration parameter, as we called it, was not decelerating at all. The expansion of the universe actually appears to be accelerating.
But the other methods
the interesting thing about that, though, is that I had been attending talks on large-scale structure in the 1980s, and there were inklings of dark energy there, because the computer simulations of the formation of superclusters of galaxies just didn't look right unless you put in dark energy. And it was not that anyone was claiming this was a discovery, but on the other hand, it's kind of looking like this lambda term that Einstein put in and then took out and all that in his theory isn't zero like we thought it was. And then the much more direct evidence of the accelerating expansion came along. And so now
but there's two questions here about what you say. First, you've calibrated the very distant ones using other methods, which I think you mean the Cepheid variable method, for example, which only is fairly local, right?
Well, there's many. You can also look at the angular size of the host galaxies, and there are several different.
Yeah.
And
another technique is that you can look. You can, with spectroscopy, tell what the population of a galaxy, the stellar population of a galaxy is like, and you can model that, and then you can use Poisson statistics, fluctuations in that intensity in patches in the galaxy, to tell how far the galaxy is away. That's another method, but there are a bunch.
Right. Now, but everybody is assuming, I think, without really knowing, that dark energy, the density, is constant with time. And it's the same everywhere in the universe, and it doesn't go down or up as the universe expands.
Oh, it's constant with space. It's not constant with time, and that's why the universe is the expansion rate is accelerating.
Well,
So-
it's
No, I think it is constant in time as well. The density is
it's a fixed energy density.
right.
per unit volume of space.
Yes.
And as the universe expands, there's more volume in,
Oh, there's more dark energy. Yes.
so there's more dark energy. So that the density remains constant, but the total amount increases.
Yes, which is odd, but it's only is dominating more recently because 3 billion years ago, matter was dominating the energy. So
Right.
Because the universe was smaller, and the universe doesn't make matter as it expands; it makes dark energy.
so why
Whatever
aren't
that is.
There, by the way, used to be, back before the cosmic microwave background was discovered, there used to be this wonderful steady state theory of the universe,
yeah
where
yeah.
the expansion of the universe made matter.
Yeah.
And it had the same dynamics as a dark energy dominated universe, because it was basically the same thing. The cosmology looked the same, except that instead of taking the galaxies and diluting them out as the universe expands, since the steady state universe made matter, in theory, that matter would coalesce into new galaxies. And so you would have an eternal universe with a constant density of galaxies in it.
Yeah, it was Tom Gold and Fred Hoyle, right? And they had what they called the perfect cosmological principle. They said the universe roughly is the same anywhere and at all times. So,
Yes.
and,
Yes.
but they only had to have about 1 hydrogen atom per cubic meter per century or something to be coming in. Very small growth, but then
Well, yeah, and that's why you only see the dark energy is the same deal, and that's why you only see it on the very, very largest scales.
right.
But the one of the other things about the steady state universe was that it was inconsistent with the hot Big Bang
Yes.
and the cosmic microwave background and the fixed cosmological horizon. So all of those things are wrapped up into the idea of a hot Big Bang. And
Right. Which the microwave background was a prediction of the hot Big Bang, of the Big Bang, right? And the Big Bang, by the way, the term was invented by Fred Hoyle as a derogatory term because he didn't believe it. Oh, you're Big Bang rubbish,
Right.
But it stuck.
I wanted to unpack one of the things that you guys mentioned earlier, and that's standard candle. Some of our viewers may not understand what that term is. Imagine taking a box of candles from the same manufacturer and the same type of candle, and then taking each of these candles and lighting them so that they're emitting light, and then take different candles from that batch of candles and move them a different distance away. You'll notice that as a candle moves farther away, it seems to your visual perception to get dimmer. Well, it would also get dimmer in a telescope or any other mechanism you can conceive of for measuring the intensity or brightness of the light. And all of those candles in the box of the same sort of candle from the same batch from the same manufacturer would be standardized. They're the same sort of candle, and you can use their apparent brightness as they're further away versus closer away. You can use that apparent brightness and plug that into a fairly simple mathematical physics equation to tell you how far away the candle is based solely on how bright it looks to you and or your instruments. And so astrophysicists have to figure out different mechanisms to determine how far away stuff in the universe is. And exploding supernova of a certain type seem to be, we mentioned earlier, this idea of sort of a critical mass like you have for uranium and fission bombs. There seems to be a fairly consistent critical mass for white dwarf stars to accumulate enough additional mass, either through collisions with other white dwarfs or perhaps accumulating mass from a companion star, that once it crosses that threshold, which is the same everywhere in the universe for every white dwarf, give or take a tiny bit of wiggle room, you get a supernova. And those supernovae will typically be of the same brightness because of the same underlying energy signature throughout the universe. And we could use those as a kind of standard candle to figure out how far away things like distant galaxies are.
Yeah, but let me add a couple of notes of caution, maybe being pedantic about this, but as you know, the intensity of the light normally decreases like 1 over the distance squared, okay? Now, that is true, but it's only really true if space is actually flat. And if the universe is sort of curved space, or as we go past masses which curve space, that can change the law. I mean, but I think we assume that space is flat enough over these distances that it doesn't change, or they make a correction for that if they know that.
For it, I mean, when we're looking out, you're looking out at a universe that is much smaller at very distant times than it was now, except that that small universe fills the whole sky.
Yeah.
What's happening? The rest of the universe is actually acting as a magnifying lens, and it's magnifying the distant universe that you see.
Mm-hmm.
And that affects the intensity of the light. And that is something that you must take into account in a profound way in order to figure out what's going on with these standard candles when you look far enough out. Yes.
So one of the big cosmological mysteries that is yet to be cracked, maybe somebody watching this will, a young person.
Brilliant young person.
Yeah, we'll get
unlike us old farts.
We'll get a Nobel Prize for this someday. There seems to be a discrepancy between the rate of expansion in the universe as measured by virtue of these supernova standard candles and the rate of expansion of the universe based on looking at the light that has come to us from the hot Big Bang, which we interpret as the cosmic microwave background. And these two mechanisms have given statistically significant different answers about the rate of expansion of the universe. And back to what Mike Albro was saying, one of the putative wild theories that I've seen to help bridge that gap is that the universe is not, in fact, homogeneous in terms of the curvature of space-time, that there could be superclusters of galaxies that essentially create giant voids and bubbles in the structure of the distribution of matter in the universe, and that if we are in a relative void compared to the light that has come from the Big Bang, might not have moved through primarily the same void, unlike distant supernova, which to get to us will move through the void of space coming to us. This discrepancy in the homogeneity of the curvature, the large-scale curvature of the universe, might help explain some of this discrepancy. And this is just somebody's wild idea.
When we look at those two numbers, each number is well supported. There's that number that says 68, and there's that number that says 74, and each group is saying we have the statistics that says this number is right. They're both correct.
Joanne, one number comes from very early days of the universe, very far away and long ago, and the other is more recent because it's based on more recent things. So the discrepancy assumes that you know the history of the dark energy, for example, and how it's changed and not changed with time, right? And it's as I say, dark energy is a large volume thing, and we're not able yet to say whether it is really homogeneous and so on. And we would like to, for example, it may be that the dark energy is actually less dense in galaxy clusters or mass than it is elsewhere. It could be anti-correlated with dark matter or something like that. I'm just sort of throwing ideas out there.
Right.
And then other ideas that maybe the Higgs field is different very far away, and that gives the electrons a slightly different mass, changes the spectroscopy. I mean, one can think of half a dozen different things which need to be, all argued about.
Yes, we're incredibly ignorant.
I just personally think that.
Let us inject a note of historical caution. I recall when the argument wasn't between 68 and 74, but was between 50 and 100.
Yes.
Yes.
We're getting a lot better.
Yeah. But about dark, I just think that the Nobel Prize given for the discovery of dark energy, quotes, was very, very quickly done and quite out of sync with not giving the prize for dark matter discovery to Vera Rubin, especially, you know. And dark matter is something we're absolutely sure about. You know, we don't know what it is, but it's there for. And she measured with Henry Ford the rotation curves of many, many galaxies and established really that it's there. And yet she never got the Nobel Prize. She died 2 years ago without getting it, which was sad.
It is a travesty. You know, this sexism has a dark and long history in academia. You know, up until
not just academia.
Well, that's true. Thank you for clarifying that. You know, it was within all of our lifetimes
Yes.
that many colleges started admitting women to some graduate programs and awarding professorships and PhDs to women in certain fields. So it's relatively recent that rampant sexism kept the lid on the recognition, at least, if not the actual contributions of a lot of female scientists like Vera Rubin and the other Harvard calculators. They're called
Yes.
calculators. They were hired because of their intellect and acumen in other area with respect to other things. And some of the most
And then
profound, and they're what?
And then ignored.
And then they're, well, largely ignored in terms of prizes, although, you know, there are quite a few modern books about science and specifically astronomy. These calculators worked in the field of astronomy that are beginning to sing the praises of some of these women like Vera Rubin. And then there was also Fred Zwicky, I think.
Now Zwicky, okay, so he first talked about dark matter, but he actually got it wrong by a big factor. He looked at clusters of galaxies and said, well, they've been around for a long time. There should be more matter there than we know about. And he got it wrong by quite a factor. And then actually he died, I think, just about the time Vera Rubin started her studies. So he wasn't so convincing, in fact. But I think the biggest anomaly ever in physics was probably Lisa Meitner, who discovered nuclear fission, right?
Yes.
She realized that the uranium nucleus could be split apart, releasing more neutrons. And this gave rise to the whole, you know, nuclear weapons, nuclear industry, and so on. And she was skipped over for the prize. She was a German Jew working in Sweden, actually, and her boss was head of the department, Manus Sigbahn, who had it in for her somehow. I think he was jealous about her, and he blackballed her really. So she never got the Nobel Prize for that, which was actually
Rosalind Franklin, right?
No, but Rosalind Franklin died before the prize was given to Watson and Crick.
Oh, did she? Okay.
Yes.
Ivan, I wanted to bring you into the conversation a little bit. I know that you've studied general relativity. Can you give our viewers a little bit of maybe background about what this lambda term is that John was talking about?
Well, it's been a while since I studied general relativity.
That's all right.
I'm not sure I have a simple way to describe it, but maybe John.
Well, let's.
Cosmological constant, yeah.
Yeah. Well, Einstein's general relativity describes the dynamics of space-time and how it responds to the energy and other things, what we call it stress, of the other stuff in the universe. And it doesn't have anything to say about the other stuff. You want electromagnetism, you have to put in a theory of the electromagnetic field. The lambda term that Einstein came up with is the simplest field you can put in. It is the simplest kind of other stuff. It merely has a constant density per unit volume and a negative pressure, which relates to the fact that it has constant density. It's negative pressure because to make more of it, you have to make more space, and that means that it's trying to pull space in, if you like. So it has negative pressure, and that goes into the to the theory also. That's part of the stress, and that's really all you can say about it. It's the simplest thing you can throw in, and we have a cosmological estimate of what its mass density is, and we know absolutely nothing else about it.
So Einstein originally used his equations to create a very simple model of the universe. And in order to make the universe static, he added this term. And then when it was discovered that the universe was expanding, he was like, oops, that was a mistake. I should not have done that.
Yeah, the other reason he called it a mistake was that it did make you could make a static solution. That static solution was dynamically unstable, and so it was static in the sense that a pencil exactly stood on its point will stay upright forever, but that was the other problem with it that he didn't realize at the time that he proposed it.
And now it seems that our vacuum of the universe is also metastable, if you like.
Yeah.
So this is actually, I gave a lecture on Thursday night to the Theosophical Society about miracles in the universe. And one of the miracles is about vacuum stability, because we've now measured the top quark mass and the Higgs boson mass, and you put them, and they're related, theoretically they're related to the vacuum's properties. And when you put them on a graph, you find regions of the graph where the vacuum is stable, regions where it's unstable, and a narrow region where it's metastable. And the points we measure lie in that region. Now, what that means is that the vacuum we live in, the universe we live in, is not the lowest energy possible vacuum. There's a lower energy vacuum state that we could tunnel into by some unlikely fluctuation, but maybe in a large time it will happen, and the whole vacuum would change. Now, of course, there's lots of unknown physics between there and now, so here and there, so it may not happen, but it's a remarkable observation that the top quark mass and the Higgs boson mass happen to lie in this region where it's calculated the vacuum itself of space is actually metastable and not the lowest possible state, which is one of the remarkable things. I gave this lecture about many so-called miracles, which are things in physics that we know are true. They didn't have to be true, but they are and allow us to exist, because if they, for example, how carbon was formed by the Hoyle resonance, that's a whole interesting story, and how the neutron is a bit heavier than the proton and so decays. And it could have been the other way around, and then the protons would decay and we wouldn't have free hydrogen and everything would be different. And these are sort of, I talk about that for an hour or so. It's I might give it a Science Sunday one day if you want to have that sort of talk. But there's so many things. It's called like the Goldilocks principle applied to the universe, how our universe happens to have just the right properties to allow life to have evolved and to exist. It's quite food for thought.
So, Michael, I have a question about these vacuums. So if you have a stable vacuum, what would that look like? What would be the difference? Obviously, if I understand correctly, our theories today rely on this metastable vacuum to explain perhaps inflationary cosmology or the masses of particles. But what would we see if the vacuum was stable? Just different physics? Well,
it's getting way outside my comfort zone here. But if the vacuum that we live in decayed by some part of it fluctuating maybe by some fluctuation of the Higgs field or something, to this other lower energy vacuum, and it would propagate. I would have thought at the speed of light out, but somebody said, no, it's instantaneous. I don't quite understand what's going on there at all. But all I can say is that if the vacuum changed from the one we live in, the so-called false vacuum we live in, to the true vacuum state, which is low energy, everything would be different. I mean, particles, masses would be different and so on, but everything would be different. And if it did happen to our universe, and it seems it could. I mean, we want to measure these masses more carefully. I can easily, showing the screen, I can show you the graph of that, but it's a very interesting thing. But one of the most remarkable miracles, I would say, that allows carbon to exist is, stop me, Scott, if I'm rambling on too much about this, but it's this Hoyle resonance forming carbon. You know, carbon is the one atom that is allowing complexity at the level of DNA and RNA to exist. No other atom, no other molecules or atoms, sorry, no other atoms do that. So, and the carbon wasn't formed in the Big Bang. The Big Bang produced only hydrogen, helium, and a bit of lithium, nothing else. It expanded too fast. So all the carbon has come from stars, very hot interiors of stars. And how did it happen? When you had helium, you had to get 3 helium nuclei together to fuse together and to form carbon. Now, that can only happen in 2 steps. 2 heliums fuse together to make beryllium, and the beryllium has to grab another helium to make carbon. But that beryllium nucleus is very unstable, and it's not going to live very long. And for it to live long enough to grab another helium and make carbon, the carbon nucleus has to have an internal energy excitation of 6 point something electron MeV. It's a very narrow window. And Fred Hoyle said the only way he could understand how carbon could be formed in the universe in anything like the quantities we see, if this carbon nucleus has an internal excitation resonance, which is to do a strong interaction between protons and neutrons, balanced by the electromagnetic interaction, complicated thing, but he predicted the energy of this thing. And he was over at Caltech talking to Willie Fowler, who's an astrophysicist there, and said, Willie Fowler, I think there must be a resonance there in the oxygen, in the carbon nucleus, and not one in the oxygen nucleus at the same place. And so Fowler got a young graduate, a young researcher to look for that. They found that resonance just where Hoyle had said it was, a very narrow window. Yeah, it's a remarkable thing. So if that resonance had not been there in the carbon nucleus, with that sort of energy, there wouldn't be enough carbon around to form life. Or, you know, and it's one of these amazing things that allow us to be here, like the neutron being heavier than the proton. You know?
It is the only prediction that has ever, the only scientific prediction that has ever been made and proved to be true from the anthropic principle.
Yeah, although actually Hoyle didn't think about the anthropic. It was retroactively, yes, but because Brown and Carter came up with the anthropic principle later. Hoyle just wanted to know how much carbon. He says, I know there's a lot of carbon in the universe. How could it have been formed?
Right.
I don't think he thought, oh, well, life is here, therefore, you know, blah, blah, blah. But so later, that was linked to the anthropic principle. Yeah.
Well, just think of it this way. Without carbon, there would be no organic chemists.
I think there would be no life, actually, I think, you know, because...
Well, heck with them. I'm worried about organic chemists.
You want about your job.
Speaking of chemistry and life.
Yeah, we have a question from our audience. They're asking about this flattening the curve idea having to do with COVID-19. Would any of you guys like to talk about the statistics of disease and spreading and flattening the curve and all that kind of stuff?
Well, they specifically want to know why the media isn't talking about flattening the curve anymore.
Well, I thought we should figure out what it was first.
Oh, I see. Okay.
Well, the curve, I presume, okay, somebody may want a bit more.
Disease curve.
Yeah. But if you talk about the graph of the number of infections per day, for example, okay, per day, so it goes up and come down. Yesterday could be less than the day before, but in order for the thing to get really under control, you have to have fewer than, so one person infected is not going to infect two more. If one person infected infects two people and they didn't infect two, you've got an exponential growth and it's rising exponentially.
That's not a flat curve, right?
No, that's
Not a flat curve. A flat curve, well, are you talking about the number of people who are infected or the number of new infections per day? Big
well,
difference.
this whole idea has been the thing that we know that under normal circumstances, a disease will come in, and if it's going to be highly infectious like this, it's going to be a rapid increase in the number of people who are inflicted. The number of deaths is going to go up concomitantly. And the idea is to, rather than have it go way up and kill a lot of people, to spread it out over time, hoping to keep the number of deaths down. And they're asking why the media isn't really focusing in on that. And of course, the first thing is, what is the idea of flattening the curve to begin with? And I think it's more of a case of, well, as we've been talking recently, we saw an explosion. For instance, New York's great explosion of all of a sudden, thousands and thousands of people. One person doesn't infect one person infects two or three or four. And suddenly we have this curve going up, just huge, monstrous numbers of people getting ill. And the people who are ill are then going out and getting other people ill and so forth.
So that's both the curve of the number of new infections over time. It's the same profile as the curve of the total number of infections.
And then of course there's that underlying curve there, which is the number of people who died from it.
Right.
The danger.
So part of the motivation for flattening the curve, not necessarily to reduce the total number of deaths over the next decade, but to slow down the rate so that hospitals can cope, because in New York, hospital couldn't cope. They were totally overwhelmed. So we have to slow down this. It may not be reducing the total number integrated over years, but we have to slow it down. And then hopefully we'll get a vaccine at some time which will reduce the infection rate. But as long as the anti-vaxxers don't say we're not going to take this because we don't believe in vaccines, if a lot of people do that, then it's going to be with us for decades, you know.
And then the anti-maskers who deliberately go out and not only infect themselves, but infect others. In fact, we have to suggest that the President of the United States would probably not be in the position he's in right now were he to have worn a mask.
Yeah. I mean, that simply, as has been said, if everybody linking with anybody else is wearing masks, then it can be brought right down until, you know, so that we can start opening up things.
A person asked me, well, why do you wear a mask? It's only 75 or 80% effective. I said, fine. I wear an 80% effective mask. You wear an 80% effective mask. Between us, there's only a 4% chance of infection.
Yep.
I'll take that.
It's more than 80% effective, isn't it? A normal.
Assuming that we're both at 80%, which isn't a really good mask, but we'll admit that. But still,
if we wear a 90% one, then the product comes down to 1%, right? Over the. So yeah, I mean, obviously it's.
May I address the question, which is why aren't the media talking about this? And I think part of it is that what we've seen worldwide is that in most places, now the United States is a place where we've flattened the curve, but we haven't really done much better than that. But in a lot of places, they haven't just flattened the curve, they've knocked the curve way down. And so, you know, it's now a more nuanced and more complicated landscape. And flattening the curve, which I think was a thing that confused a lot of people to begin with anyway, is not really what we should be talking about. We really, we understand that it is possible and desirable to knock the curve way down. And so I think that's part of the reason why you don't hear too much about flattening the curve anymore.
We have not really flattened the curve in this country.
Part of the issue with hospitals being overloaded is that it affects the mortality rate. That right now, I think the estimate is that the disease has something like a 0.4% mortality rate. But if the hospitals become overloaded, then it can go up into, you know, maybe, who knows, 3 or 4%. So by keeping the curve, by flattening the curve so that the hospitals are not overloaded, you're probably saving a lot more lives by doing that. But I assume that the media won't talk about this very much if the hospitals are not overloaded. I imagine if more hospital systems were overloaded, it would be a bigger factor in the news.
Agreed. Yeah. See, I don't see any other questions. I wanted to do a thing, and I brought props. Last week, the question was asked, why do we have a kneecap, but we don't have an elbow cap? And none of us wanted to talk about it. So I was messing around with my brain, got into low gear, and I just couldn't give it up. So I'm going to play a game. This has nothing to do with reality. This is just my interpretation. So all of you who are out there who actually know something, please forgive me. But we're going to talk about
here, so she can't object.
Yeah, we're Abby here. I would give her my 2 pencils. I have 2 number 2 pencils, which is not the same as 1 number 4 pencil. And we want to think about this in terms of a lever, or is that lever? Which
Lever.
do we prefer? Lever?
Lever, for English anyway, lever.
Okay. So when we think about a lever, we think about a long pole and a fulcrum. And there's that old story about give me a place to stand and a lever long enough and I will move the world. Well, true. A lever can be this kind. This is a primary lever where I have a short section and a long section. And I put the short section underneath something and I pull on the long section. And simple math. The distance times the weight equals the distance times the weight. I can move a refrigerator. Little old me, I can move it very easily. Give it a long enough lever and the fulcrum to place on it. Now, if I look at the human body and I say, how many primary levers do we have? We have 0. We don't have any. But I can also turn this around. I can do this and say, I'm going to pull on the short end of the lever. Now, what is the advantage of this? Well, the advantage is, of course, I have to put an awful lot of effort here to make this move. So again, my idea, I have to put down 10 pounds,
Hold it up for the camera.
10 pounds to make it move 1 pound.
Hold it up for the
But
camera.
We
I'm
can see
trying-
it. We can
I
see
really am.
Okay.
I'm really trying to.
We can see it.
But my hands are in my face.
Oh, right.
So now, what do we have that corresponds to a secondary lever in our bodies? Well, this is one right there. We have this beautiful long bone, the humerus, and we have 2 bones here. And we know this is from 320 million years ago. This bone simply allows us to turn the hand. This bone is the fixed one. It sticks out on the end. It sticks out because we have this beautiful tendon back here. This is an enormously powerful tendon, and it allows us to do this. And we have a powerful tendon here that allows us to do this. And this is one of the secrets of humans. We can throw things. We are really good at throwing things. Baseballs, footballs, basketballs, javelins, spears, all those kinds of things. And our relatives, the chimpanzees and the gorillas, do not do this. If they have a stick, they will do this. We will do this. And there's that motion. So again, a 2nd degree lever. The other one we have is in our ankle. And again, 2nd degree lever. We're using a lot of force to get a tremendous amount of motion and speed. If I move this 45 degrees, this moves 45 degrees. This moves 3/4 of an inch. This moves 7.5 inches. This moves in 1/10 of an inch, 1/10 of a second. This has to move the same thing in 1/10 of a second. I can get enormous amounts of speed with this kind of an action. And that's this. Also, this ankle. That's the only 3 we have. Everything else is this. A ridiculous system where we stick the 2 ends together and pull. It's a ridiculous, it doesn't work well. What it does do is it allows huge amounts of motion, just enormous amounts. And that's most of our system. Now, why do we have coverage on the knee but not the ankle?
Coverage.
Coverage. I'm a patella.
Oh, the kneecap.
That's the one.
Okay.
Because when we're walking and moving, the elbow is behind us. It's not out front where it's going to get hurt. We got these things out front, so hopefully this thing doesn't get hurt. The only time it gets hurt is when we back up, and we have no good backup lights back there. We have no good mirrors, so we're walking around going bang, and it hurts when you do that. So the objective is don't do that. But when you're walking, especially when you're running, the knee will actually project in front of the foot. So you place your foot down, you straighten your leg up, and the knee will come out front. You got to cover it. There's 3 bones there. They're coming together. And if those 3 bones smack into something, you stop walking. And you could stop walking permanently. The patella takes that energy and spreads it out over space. So from what I can see, the patella is there strictly as a defense mechanism. Most animals don't need it. But then again, we're the upright people. We're walking around doing stupid things with our knees.
So horses don't have kneecaps?
They have they have a thing.
Yeah.
But it's not like a big fat thing like we get a big fat thing,
Okay.
a beautiful patella. So everybody has a little, but we got robust patellas and we can throw things.
So it's because we lead with our knees.
We lead with our knees, but we don't lead with our elbows.
Right. Okay. That's a good idea.
But, and again, the whole idea of primary, secondary, and tertiary levers. This is us. I mean, there it is.
Hey, Joanne, that's interesting. Did you figure all that out?
As I said, it was one of those things that was bothering me, and I had 2 pencils.
Yeah.
So I could do this.
Maybe we can see next time in 2 weeks if Abby has.
If Abby's here.
Abby has other examples of human physiological capabilities that are fairly unique.
And she could also critique my amateurish discussion.
Wow.
Well, it's Halloween, so there'll be a lot of human skeletons around that we can look at. And
Oh, yes. They're fascinating.
Yeah.
Because when you look at, the construction of the human body, it's silly. All the silly things that have, like the dumb nerve that comes up here, goes down around your heart and comes back to get to that distance.
you would have done a better job, Joanne, would you? You would have done a better job.
You would have been a more intelligent designer, is what I'm saying.
I think I could have engineered a better system.
Yeah.
A lot of better systems.
Well, Abby wrote a whole book about this, so.
Oh, yes. That's why I'm.
Yeah.
I feel silly stealing her. I mean, she knows this stuff.
It's just
really.
because she's not here today, isn't it?
Yeah, I get to be the Abby today.
So did we have other questions? We're not seeing questions, are we? Do we have?
No, Mike, I've got a chat link on another screen to Dave, who's moderating and watching the YouTube stream. So if any of our guests on YouTube have any questions for us about science, the philosophy of science, the conflict between science and superstition, science policy, anything that is along those lines, we're happy to take your questions. I do have another topic. One of my favorite topics is astrophysics. So often that's kind of where I lean with some of my research and inquiries and learning. But speaking of learning astrophysics, one of the things I saw recently was confirmation of a new rogue planet that's about the size of Earth. Rogue planets are planets that do not orbit a star. And the theory is that during the formation of solar systems, not necessarily our solar system, but solar systems in general throughout our galaxy and throughout the universe, some of the dynamical processes driven by gravitational interaction can have the result of ejecting planets from a forming solar system. And there are estimates that there are more rogue, some astrophysicists have speculated that there are more rogue planets in our galaxy than there are stars in our galaxy. And I think 4 have been found so far, but this is the first one that's been found that is about the mass of Earth. And
How has it been found, Scott?
I'm sorry, what?
How has it been found?
Gravitational microlensing.
Oh, passed in front of a star and dipped the light in.
Right.
So can you give us a reference to that article? Is it a?
I don't have it handy with me here on our chat, but I can
check it out. Though it's interesting. I hadn't heard of it, that new one. It has been speculated. Yeah.
Oh, we all heard about rogue stars. And that's, okay, sure.
Yeah. There's a rogue star that has been discovered passing through our galaxy.
Yep.
That according to its speed, it has an escape velocity that will take it beyond the gravitational grasp of our Milky Way. And so it's a rogue star that's bound for interstellar or intergalactic space.
Yeah. Wandering around someplace.
So
let me make one more comment here, and that is that microlensing makes the star behind the lens look brighter, not dim.
Right. It actually has an up and down curve, right? It goes up and doesn't it go down on the other side? Anyway, it brightens it.
It's like a telescope. It magnifies the light.
Yeah. But if you had a rogue planet or a dark invisible star that passed through our solar system, it would perturb our planet's orbits in a way. But I don't know if anyone has calculated a limit on the number of such things passing through our solar system, because the orbits have not changed, as something goes through it.
Well, you snuck in the idea of a dark star. Could you tell me what you mean by that?
Well, I mean, it doesn't have to be a black hole. It could be a neutron star by itself. Okay. But, I mean, neutron stars we usually see because they have magnetic fields and they're spinning rapidly and blah blah blah. But neutron stars,
hot. They have thermal radiation because they're still cooling off. Right?
Well, but they get old and cold.
They get old and cold, yeah.
Not in the life of the universe, though. There's still there are no such things as black dwarfs, which are the putative end of a white dwarf. White dwarf will eventually cool.
Is that a racist comment?
No, not at all. It's just about light spectrum.
Are you saying that a white dwarf will not become cold and dark in the age of the universe?
Not in 13.8 billion years. It has not had enough time to cool off to the point where it's not emitting visible light yet.
You can say that fairly well, because white dwarf matter isn't all that different from the stuff we're sitting on, but neutron star matter is something very different, and we don't understand the heat capacity of it.
Great.
Okay, so then you could have black holes with a mass of the planet, a mass of the Earth black hole, which would be invisible if it's not near anything else, right? It would just
people
the size of
be such a thing in the outer solar system.
Yeah, a black hole the size of the Earth would be the size of a marble as well. Or a golf ball, I think.
Just something in.
Yes, yeah, it's something. That's right. That's right.
The these
we don't see gravitational perturbations from extrasolar stuff passing through the solar system.
Right.
And our ephemerides are so good now that we could see something down to a pretty small mass. I don't know exactly what. But what we have seen in the last few years is we have seen 2 asteroids or comets, whatever, two minor planets drift through. One of them.
Oumuamua.
What?
Oumuamua.
Oumuamua.
Yeah.
Yeah, that one was an odd one. And then there was Borisov, which looked like a routine comet, except that it was zipping through far too fast to have come from the Oort cloud, falling in. So, yeah.
So about small black holes, this is the answer to our energy problems forever. Because if you find a black hole with a mass, I forgot exactly what it is. It's like 1,000 tons or something like that, and it's very small, like a pea or so. And if you can catch one and could in orbit around the Earth, its temperature is, let's say, 1,000,000 degrees. Now, it's going to be radiating and losing mass, but you can stop it doing that by throwing trash at it and keeping it at that mass and keeping it at that temperature. And now you've formed a thing, a black hole. You've kept it in orbit around the Earth. You're feeding it with mass, rubbish mass, or anything you like, just to keep it at the right mass with the right temperature. And it's radiating this hot thing. It's like a star in your orbit around the Earth. And you can adjust the temperature by deciding exactly how much crap you want to put into it. And, you know, you can keep it stable. Of course, the problem is you've got to find a black hole with that right mass and capture it and put it in orbit around the Earth. But then run that, that's an exercise for students, right?
You're sort of proposing a cosmic dumpster fire then, aren't you?
You're turning mass into energy with 100% efficiency, and you can put any fuel you like into it.
I think it's 50% is the maximum. So some of the mass must get inside the event horizon, but about 50% maximum of the mass can be radiated away as energy. But that's not the Hawking radiation. That's just the accretion.
The point is that if it's small enough, it's radiating the rest of it as Hawking radiation.
Right. That's true.
Yeah. That's
Wow.
So yeah, it can be 100% efficiency. You just got to stop it exploding. If you stop feeding stuff in, it will explode away. But
Yes. But you know, the truth is that 50% would be entirely useful.
yes, yeah.
Oh yeah.
But I do believe that the regulatory hurdles for placing such a thing in orbit around the Earth would be difficult to overcome.
Yeah. And how can you steer it? You know, you can only interact with it gravitationally. So it's anyway.
Well, there is the idea of Newman black holes, if I've got the name right, that are electrically, or that have magnetic fields at least, where the magnetic field, so the conservation of energy, you professional physicists can correct me on this, but the way I understand it is when a star that has an intrinsic magnetic field because of the plasma churning around inside the star, nearly every star, if not every star, will have a magnetic field. And the conservation of energy in the electromagnetic field implies that as the star collapses into a black hole, those magnetic field lines will, in a sense, in some literal sense, depending on your relativistic frame of reference, those magnetic field lines will be forever frozen onto the surface, the geometric surface of the event horizon. So you can get black holes with magnetic fields, even though the magnetic fields don't, in some sense, propagate inside to, quote, the core or the singularity. They're just frozen on the event horizon. And that could be make for really interesting relativistic magnetohydrodynamics. Ooh, that's the $4 word.
This, but it must require some non-standard theory of gravity, because there is the famous no hair theorem that says that a black hole of the type predicted by general relativity can't have a magnetic field.
So it can have so it can have charge, right?
You can have electric charge, and it has mass and electric charge, because these things give lines of force that go out way beyond the.
And then a spinning electric charge would give it the magnetic moment.
I don't know. Yeah. Are you saying, John, that a classical black hole does not have a magnetic field outside it, even though it's got an electric charge and an angular momentum?
Yes.
Oh.
Okay. I didn't know that.
How?
Mind bending, isn't it?
Yeah, if it's moving and rotating, how can it not?
Rotating. What's rotating? That's
Angular momentum. You know, it's got an angular momentum, right?
Yeah, but what stuff is rotating, and where is the magnetic field?
Well, there's the photon horizon. Isn't it the photon horizon around a Kerr black hole? So a splitting. Let me back up a couple steps.
Go ahead.
So Einstein's field equations for gravity, one of the first people to make a solution for them was Schwarzschild. I don't remember his first name. But we assign his name to the Schwarzschild radius, or the event horizon of a black hole that's just boring. It has no other feature other than gravity. And then there's a so-called Kerr black hole, Kerr, and that's a black hole that is spinning. And it's believed that every astrophysical object in the known universe is likely to have angular momentum, and to have conserved angular momentum during its collapse. So we would have spinning black holes. One of the other implications of general relativity is that a spinning mass, in a sense, drags the fabric of space-time along with it. It's called frame dragging. Yeah. And there are several implications of that about that have to do with the orbit of non-powered particles. I think it's something like 2 or 3 times the distance of the event horizon. If you're a non-powered trajectory, you are inevitably going to fall into the black hole. If you're within it.
When the observation of these coalescing supermassive black holes, was seen with gravity waves, they worked out the general relativity of that very well, and I think they know the angular momentum as well as the masses of those 2 black holes and their radii, because as you point out, a spinning black hole, the gravitational field is not isotropic like in all directions. It's actually there's a magnetogravity right. or gravito-magneto effect or something like that.
Right.
But yeah, black holes have angular momentum because angular momentum is conserved, and as this collapsing from a star, it's conserved. And right, so yeah, they do have. But as far as magnetic fields, I don't know about that.
Yeah, maybe I'll have to. Maybe next time we meet, I will have done a little more research on that and see if I'm full of hooey about the frozen magnetic field lines. Maybe the magnetic field just vanishes.
We had a question on coming up from one of our watchers. They were wondering about a rogue planet entering our solar system, and how close would it have to get before Earth would be disintegrated,
oh my goodness,
or damaged or upset in some way. Especially for a similar size, assuming similar size to us.
Well, I can say that even an object that is the size of a small hill or a small mountain, if it came too close to us
and hit in Yucatan,
and hit in, say, the Yucatan Peninsula area or some other shallow ocean and whatnot, it could cause enough damage through the heat released as it fell as a meteor. You've seen meteorites in the sky that glow. They're on fire. You see them shooting across the sky. Well, that's the frictional heat of the atmosphere. And if you have something the size of a small mountain, maybe a kilometer or 2 in size, that were to hit the Earth, much less something the size of the Earth, it could do enough damage to cause an extinction. And that's happened at least once in our planet's history. And that's just a small mountain, not a whole planet.
If you think of a rogue planet that's entering the solar system, say it's way out by Mars, Neptune or something like that, think if you're sitting on that thing and you look at Earth, you see how tiny Earth is at that distance compared with the whole sky. And you have to be hitting that target, really, because if you miss Earth, you'll just go around it. You won't be dragged into it.
Yeah, they'll do a dance around each other, right?
Well, you won't dance around. Well, you come in and go out again. What comes in must go out, unless it's perturbed by the orbit by the moon or something like that. It's very unlikely to actually hit Earth. And you can see that the probability is something like the area of the Earth as seen from the planet compared with the whole sky area. It's very small. Now, of course, for meteors and so on, there's so many out there, they nearly all miss, but some do. Meteors are hitting us all the time, small ones, yeah. But anyway.
How many Earth radiuses do you think it would take for again, an Earth-sized object to cause us to wobble in our axis, to cause us to change our orbit? How much?
how
Okay.
close would it have to come?
I
Yeah.
just did the back of the envelope calculation, and if you had an Earth-sized object that passed within 10 Earth radii of the Earth, it would raise tides on the Earth similar to what?
Huge.
I'm sorry. I did it upside down, didn't I? I want to go farther out, not closer. Yeah. No, it has to be like 1,000 Earth radii. Yeah. 1,000 Earth radii of Earth. It would raise tides similar to what the moon does.
And anything
Yeah,
closer to
Joanne's
that.
point, the damage would be huge. It doesn't have to hit us to do enormous damage and
Yeah.
maybe perturb our orbit, and
Well, I don't think it depends on how fast it goes through. But I think the big thing is that if you had a large tide, you'd do a whole lot of damage.
Right.
Well,
And the
presumably,
effect on the moon would be enormous as well, because the moon's just a tiny little thing relative to us.
Yeah, it depends a lot on when it comes through and whether the moon's on the same side as the thing that's passing through, or it's on the other
And
side.
I
the
would just
interesting
want-
thing about this question is that all of these prospective answers can be addressed with Newton's equations. We don't even have to use Einstein's general relativity.
yeah.
I think
M1,
one
M2 over R
risk
squared.
would be is it passes through or near the Oort cloud or even the asteroid
Oh,
belt.
yeah.
Yes,
It
yes.
might fire all sorts of things through the solar
There's a lot of
system.
comments through. I actually had the privilege of sitting next to Jan Oort on a bus in Holland when I was at a conference. Oh, this was, I don't know, 40 years ago or so. And we were at a conference and I happened to sit next to him on a bus. So that was really quite exciting. But yeah, we can calculate, when you imagine how we can calculate the orbits, send off Pioneer and Voyager spacecraft, and we get it exactly right so yeah, if we see this rogue planet moving, we can say what it's going to happen to it in the next 100 years or whatever. But
We have another question on YouTube, also about extra solar planets, as it were, and that's about SETI. Is there energy? Peter wants to know if there's any energy being put into SETI. Well, there's certainly money being put into it. Paul Allen, who recently passed away in the past year or two, one of the co-founders of Microsoft, invested heavily in radio telescopes that have as their primary task looking for signals coming from potentially communicating extraterrestrials. And they're looking at, I think, the so-called watering hole. There's a
Yes, I heard about that.
region of the radio spectrum where radio waves can move fairly uninhibited through vast interstellar distances, unperturbed by the kinds of junk you find in between stars generally. So there are many different ongoing surveys for SETI, which stands for Search for Extraterrestrial Intelligence.
I'm still trying to find intelligence on Earth. So
Yeah.
yeah, I have an interesting thought about this, because suppose that you were an advanced civilization of the sort that might radiate radio within, let's say, 100 light years away, okay? And they are now listening to our broadcasts, and they are seeing newsreels of the First World War, and they are thinking, we better stay quiet because that's a rather nasty place. So
they're nasty people.
We didn't broadcast newsreels of the First World War.
Yes, of course they were. Well, not TV, but radio. Okay.
Radio.
Right, radio. Yeah, there were radio programs.
Well, there weren't. The first radio programs were actually in the 1920s.
Oh, I see.
Okay.
Okay.
They could listen to military communications in Morse code if they could.
Yeah. Well, if they're only 70 light years away, they could hear the Second World War. That would be.
Well, the 1920s is 1 century ago.
That's true, 100 years.
Yeah.
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 Right. So
Wow, time flies when you're having fun.
in place.
Wow. I had an uncle
The
who.
device was made in the 1930s.
Yeah. In the 1930s, my uncle was working on Marconi's radio ship, actually. And then in the Merchant Navy, he was sunk by a U-boat, and he died before I was born, but sunk by a U-boat. But he was a radio operator on Marconi's radio ship.
Okay, I've got a back of the envelope challenge for you, professional physicists.
Let me find an envelope. Hang on.
All right.
I have the pencil.
All right. So let's say that we've got a standard sort of terrestrial transmitter transmitting a TV signal or a radio signal to our audience. And then we're at a star that is, let's just say 10 light years away.
Oh, that's close.
How big of a radio receiver would they need to get enough signal amplification that they could detect the kind of sort of 1 megawatt signal that comes from a standard TV or radio broadcast?
Yeah, well, I'll need to do that for next week, but you know, you have to see how many photons can they get 1 photon per hour sort of thing to their antenna? No, because they'll have
radio. It's not photons. It's thermal. You worry about what their receiver temperature is.
All right. Okay.
I'm a spacecraft designer, among other things. I do this.
Okay.
So you answered then. Okay. Yes.
John, tell us.
It takes a little while.
Yeah.
It's a little bit more complicated than the back of an envelope.
Okay. So one of the
So they're not watching I Love Lucy?
one of the anecdotes I heard is that if you had
I remember that there was a paper in Science. Oh, what? It's probably 45 years ago now that went into this in detail, and the answer was that the antennas were really enormous. They were not beyond the capability of a civilization that could build continent-spanning structures and things like that, but they were beyond our capability.
right,
Now,
much bigger than Arecibo.
Right. Now, the thing that is within our capability and would be within the capability of a similar civilization 10 light years away is to detect the fact that we were broadcasting television. We're hardly broadcasting television at all anymore. The old-fashioned television signal had very low entropy, actually, and so that there were, if you took a spectrum, there were enormous peaks at certain frequencies in order to synchronize the receiver with the transmitter, and that with Arecibo, you could from 10 light years away, you could figure out. So you could figure out what they're with, if they were broadcasting second half of 20th century style television, you could figure out how many lines in their frames they had and what frame rate they had and all that. Cool. But you couldn't actually see the pictures.
But you'd have to be directed, right? I mean,
they'd
have to have an antenna that's directing at Earth, listening to that, and see what actually,
and that's only 10 light years away.
Right.
Most of the galaxy is thousands of light years away.
Yeah.
We routinely
one of the big things in this so-called Drake equation about how many stars out there planets out there could there be. One of the biggest unknowns actually is how long any civilization lasts that's actually broadcasting or sending out and using radio, because we've only been doing it for about 100 years, since 130 years or so, out of the 3 billion years of life on. And maybe in 100 years or 1,000 years, we're just not going to be doing it anymore. Maybe our civilization won't be like that. We won't be using, and so that's a tiny period. And it could be a rule that when you have a civilization that grows as fast as ours has, largely using fossil fuels for energy, okay, coal, oil, gas, we're burning it all up. We cannot be doing that for a long time. We have to, because it's just not going to last for a long time on the scale of the hundreds and thousands of years. So maybe, the civilizations collapse before lasting for thousands of years, which they would have to do for that Drake equation to have any chance of.
Well, and the other thing is that that analysis from 45 years ago is already obsolete because we're not broadcasting television like that anymore, and the digital television that still is broadcast is much less conspicuous because unless you have detailed of the ability to see the signal in detail, it just looks like random noise.
Yeah.
And that's one thing that's definitely happening with our civilization. We haven't collapsed, but our use of high-powered radio is collapsing.
We're going quiet.
We're going radio quiet because we're doing much more communication using things like fiber, and our broadcast, our radio communication is much more efficient. It's putting a lot more entropy into the signal, which means that the signal looks much more like noise than it did a few decades ago. And whole areas of the spectrum are going radio quiet. I used to love listening to shortwave radio, but it's dead.
But John, we're all using GPS, right? And we're getting signals from these satellites. So they're broadcasting. All these satellites are broadcasting.
They are, but those are very, very low power
and directional.
Well,
yeah,
well,
they're aimed at Earth. Well, yeah, some of
they direct downwards, but right.
Yeah,
I was reading a paper about.
Power. They're powered by solar panels that are smaller than this room, so they're not like megawatt television stations, and the reason that it works is because the actual data rate that's coming that GPS uses is very low. I was
reading a paper about ways that the Earth might show up to other civilizations, and the number one source they wanted to use as sort of an example of how we might be seen were Cold War radars, anti-ballistic missile radars, which pumped out huge amounts of power, and they were directional, but that's, I don't even know if those kind of radars are still operating in the same way, but
they are, because space surveillance is a very big deal, and not just for Cold War purposes, but because low Earth orbit is getting so crowded that various agencies want to know where all the junk is. Every once in a while, NASA moves the space station to get it off the trajectory of some piece of junk.
John, I have a question for you about GPS, because you seem to know a lot about that. So it seems to me if there were one or two key people who actually were the origin of the GPS system, which has done so much benefit to mankind, they should be candidates for Nobel Prize in physics, right? Isn't that true? I mean, if you could pin it on one or two people, maybe.
Yeah, I don't know. I know the guy, and I'm blanking on his name. I know the guy who invented differential GPS used for precision measurements of the Earth.
So the Nobel Prize, would it be a peace prize to keep husbands and wives from fighting in their cars?
Yeah. All right. Well, by the way, as I said, the Peace Prize should go to Fermilab and CERN, because we collaborate on a worldwide nature and science. And I think we actually deserve the Peace Prize. The Physics Prize can't be given to organizations, the Physics Prize, but the Peace Prize could be. So I'm rooting for that.
I don't know that it may have been, a lot of engineers don't like to be in the spotlight.
It's true.
And even some scientists.
Yeah.
I worked down the hall. I worked in the lab with a guy at MIT who people down the hall didn't understand. I would get questions, what does this guy do? And I said, he does everything that we need him to do in the lab. But he never blew his own horn, and he was completely it was almost perfectly anonymous even to people working down the hall from him. So
Well, fine, you don't have to play your own horn together, but you have to do something of benefit to
yeah,
mankind.
I know, but my old friend and mentor Ray Weiss, who got the Nobel Prize for gravitational radiation, called it a pain in the ass.
Yeah.
Oh, that we should all have such pain, right?
Yes.
Well, but Ray just likes to go in the lab and make stuff work. That's him.
Yeah, yeah.
Well, we're at our allocated time now. We have probably an infinite number of additional topics that we can and
Always remember,
we'll try to cover in the future. Thank you for your delightful discussion of levers and kneecaps
and elbows.
and elbows. And thank you to Mike and Ivan and John for talking about mostly astrophysics and issues around extraterrestrial intelligence and whatnot. And
My apologies to Abby for having stolen her spotlight.
Yeah, hopefully she'll be back with us in 2 weeks, and we'll be back with another exciting Sidewalk Science. Thank you all for tuning in, and we'll see you later.
See you guys.
Bye.
Have a good day.